Hi, my name is Takumi Yamamoto, and I'm a first-year master's degree student at Kyoto University in Japan. I will be presenting Masktrap, designing and identifying gestures to transform Masktrap into an input interface. At first, I want to talk about the motivation of this research. Most people wear accessories around the face. One of them is a face mask. During the pandemic, it has become a necessity for our daily life, and people are required to wear masks in public space. With the increased demand for masks, various types and colors have become available for sale. Many people wear masks in daily life, so it is convenient to input information using masks. In this research, we focused on mask trap as an input mechanism. I will show you about our system overview. We implement the hardware device. At first, user hooks the mask trap on the device, and then wear the device on their ear. Finally, users conduct the gestures, and system can recognize it. I introduce the related work of this research. First, there is some research related to mask-based interface. For inputting the information, the third speech interface or detecting the breath gesture have been tried, but previous research is not focused on mask, the strap or mask. The advantage of using mask strap is two things. First, using straps afford a rich set of interactions such as playing, touching, so we can input information in various ways. Second, compared with touching the filtering mechanism, it doesn't cause bad effect on its hygienic condition. In addition, there is a lot of research related to hand-to-face gestures or string gestures, but hand-to-face string gestures are not explored. This paper has three contributions. First, gesture design. Second, is implementation. First is the technical evaluation. First, I want to talk about the gesture design. There's no research using Masktrap as input interface. There's research on string-based gestures, but that assume earphone-like strings. The position and orientation are different from this, so we cannot use them. In general, many HCL researchers conduct a user elicitation study for designing gesture. In the user elicitation study, the experimenter showed the participants the operation, for example, turning the volume up, and then the participants designed the gesture for the operation. According to Moritz et al.'s research, the gesture set designed by conducting elicitation study is more intuitive and preferable for users than the gesture set designed by HCL researchers. So it becomes a standard method to design gestures and applied in various domains. So we conduct the elicitation study for designing gestures. We asked 20 participants to design gestures. About the task to ask, now we assume users use this system in daily life. So we select 21 daily tasks from previous research. Rules for design gesture are three things. First, participants have to propose gestures only using Masktrap, not using the filtering mechanism. Second, the task has a group, for example, music, phone, and participants have to avoid the conflict of gestures within the same group. Finally, the participants don't have to consider the technical limitation when designing gestures. Next, we analyze the proposed gestures. We categorize the gesture into 6 types: pull, touch, press, click, pinch, and twist, and found that pro gestures are most proposed. In about the interaction area, we categorize the area into 6 groups. Comparing right and left, 72% of cases use the right strings. We think this was because all participants were right-handed. Comparing the upper string gestures and lower string gestures, press and touch gestures are often performed in upper straps and others in lower straps. We then calculate the agreement rate, AR, which indicates the degree of agreement of the suggestions between participants. The definition formula is shown on here, and max is 1, the minimum is 0. The higher the AR, the manufacturer agree on the same proposal. The results are shown in the diagram on the right. The average was 0.062, the minimum was 0.005, and the maximum is 0.142. According to Batab et al., which is interpreted as low agreement below 0.1, which means that many different gestures were proposed between users in this study. This means that the input using the mask strings has diversity. Finally, the gesture with the highest number of suggestions was chosen as a final gesture set. The rules for gesture conflict were two things. First, gestures in the same group cannot be duplicated. Second, not gesture can be duplicated for operation 0. Next, I introduced the system for the identifying gestures. We took the approach of detecting the movement of mask string from a reusable ear hook device. Many previous studies have attached the sensor to the mask itself, but masks are frequently used and discarded, so it is time-consuming for users to attach sensors every time. By making an ear hook device, the time and effort for users are eliminated. This device contains 8 photoreflective sensors and 2 microphones. The user wears the previous device and masks by attaching them at the same time. About the software, we apply the machine learning method to detect the gestures. In each gesture, we record the data for 1.2 seconds, and the frame length is 415 frames. After recording the sensor data, we conduct the feature extraction. For photoreflective sensor data, we extract the mean and variance values for every 45 frames. For microphone sensor data, we extract the many spectral features after FFT. We use the random forest classifier as a machine learning algorithm. For the gesture set of evaluation, 10 gestures are selected from elicitation study results. This is because the same gesture on the both sides was only used the right side, and the gesture conducted multiple times were reduced to once. In addition to these gestures, we add removing and wearing masks, and finally, 12 gestures. For the technical evaluation, 8 participants were asked to wear the device and mask on their right ear, and 12 different gestures are acquired 20 times each. The information of participants is shown in table. The type of mask is the same of all participants. The result of experiment is here. We can get 92.61% by only using photoreflective sensors, but we got only 42.40% accuracy by using only microphone sensor data. By using both sensor data, we got the average accuracy 93.07%. Now we assume this system is used in daily life, but we think this system can be used in the situation where people often wear masks for other purposes. For example, on the cleaning work in healthcare-related settings. In an experiment for technical evaluation was conducted in control settings. In the future, we will conduct an additional user study to confirm we can use this system in the real life. And we conducted the experiment for only one type of mask. So we try to change the mask type. Furthermore, we will try to investigate the gesture usability. In summary, in this research, we conducted the LHS study to explore the design space of Masktrap, and we define the data set. And we implement the hardware device and conducted the technical evaluation through a user study. Thank you for your attention.